All right, so last week we talked about two different types of materials. We said that materials are either conductors or insulators. So remember, insulators are things that electrons can't flow in. So things like rubber, plastic, glass. If you have electrons on these materials, they just stay there, right? And that's why we used the rubber balloon in order to build up a static charge and stick it to the wall, right? Or rub the rubber balloon on the wool sweater. You know, so those were static charges. Those were charges that didn't move, right? The electrons were stuck. Now we also talked about conductors. So remember, conductors were materials like copper, gold, iron, and these materials allowed electrons to move through them. So you could take electrons and you could send them down a copper wire. So that's what we're going to focus on today, is these conductors and these moving electrons. We call this dynamic electricity, moving electrons. And we use this quite often because anytime you're using electricity in your house, you're using moving electrons to do something, whether it's turning on a light or heating a stove or charging your phone. So what happens when you go and press a light switch on your wall? All right, so, well, let's start with that first question. What happens when you turn the light switch on your wall? Well, you have power coming into your house, right? There's already moving electrons that are supplied to your house. And when you turn on the light switch, you're allowing those electrons to flow. In your walls are copper wires. And when you turn on that light switch, you allow the electrons to start moving in those wires. They bring electricity to your light bulb, right? The moving electrons are electricity. That's what electricity is. It's just a moving electron. And that allows your light to work. Now, where do these moving electrons come from? How do you make electrons move? Well, you just need a very simple machine called a generator. So what a generator does is it converts mechanical energy, moving energy, into electrical energy. And it only has two parts to it. It has a magnet. Think about like a bar magnet that you've played with before. You kind of stick them together or push them, if you put it opposite, they kind of push each other away. And a coil of wire. So you take like a copper wire and you coil it around and around and around, hundreds or thousands of times. You end up with this. Those are the only two things you need. Now, this magnet, it has a magnetic field. You can feel that when you push magnets together or pull them apart. And that magnetic field will actually interact with the electrons that are in the wire. So when you move the magnet past the wire coil, it actually caused the electrons in the wire to move. So you can think of it as that magnetic field from the magnet is kind of pushing these electrons and making them move in that coil wire. All right, I have a bit of a simulation here. So here I have my magnet. Here I have my coil of wires. I connected it to a light bulb. And I have a bunch of blue dots. These are my electrons that are just on the copper atoms, and they're happily sitting there not moving. Now, what happens is as soon as I start to move this magnet past that coil of wires, you'll notice that it starts to push the electrons, it starts to move the electrons in the wire. And as those electrons start moving, they would allow the light bulb to start functioning. Now, as soon as I stop, the electrons stop moving. So if I wanted to keep that light bulb on, I would need to keep moving my magnet back and forth. And depending which way I go, it actually pushes the electrons in the opposite direction. But as long as the electrons are moving, as long as I keep moving the magnet and causing those electrons to keep moving, then my light bulb functions. Now, the magnets, sometimes they're very heavy, especially if you have a large magnet. So sometimes it's easier to move the coil of wire back and forth instead of the magnet. But it's the same idea, right? If you move them past each other, then the magnetic field from the magnet pushes those electrons. The electrons start moving. Now you have electrons moving in your wire and you have electricity. So that's all you need. If you want to create electricity, you just need a magnet and a coil of wire. All right. So as I mentioned, sometimes it's easier to move the coil of wire instead of the magnet just because it's a bit lighter than the magnet. Now, if you were to do this at home, it wouldn't produce very much power, right? If you wanted to run a light bulb, you would need a big coil of wire and a big magnet, and you'd need to just frantically move it back and forth as fast as you could. And, you might be able to create enough electricity to run a tiny LED light, but it wouldn't create much energy. So you need to do these things with very large magnets and very large coils of wire. So that's what power stations do. Right? There's a bunch of different types of power stations. There's coal power plants, natural gas power plants, hydroelectric dams where you use running water, wind generators. All of these things, they all use the exact same type of generator. They use a magnet and a coil of wire. And they just move those things back and forth past each other. So every single power generating station, except for solar. Solar is a little bit different, but all the other ones, I mentioned a bunch earlier, also nuclear, geothermal, all of those use the exact same type of generator, which is really just a magnet and a coil of wire. And as long as you move the coil of wire and the magnet past each other, you will start to generate electricity. So the question is, how do you move the magnet and the coil of wire? Because that's what the difference is in the different types of power generating stations. So you have some sort of turbine, which is really just a big metal wheel, and you connect it up to your coil of wires, and you keep spinning your coil of wire past the magnet. But how do you spin this big turbine? How do you spin this wheel? And that's where you have a different number of options, right? You could build a big dam, and you could use water that's flowing down the dam. That's a hydroelectric dam. You could use coal or natural gas, and you could burn it and boil water, and then use the steam to push the turbine. That's what happens in a coal power plant or a natural gas power plant. You could use wind to just spin the turbine. You could use radioactive material to boil water and then push the turbine with the steam. But you'll notice that all we're doing is changing how we're spinning this wheel, how we're spinning the turbine. And then in all of these cases, you attach that turbine to your coil of wire, you move it through the magnet, or you move it past the magnet, and that starts to move the electrons in the wire. You connect that up to your energy distribution grid, right, your power lines, and you send power to people's houses. Now, there's a bit more, complicated details there in how the power is sent, but that's the general idea. If you can spin a coil of wire past a magnet, you have power. You have electricity. All right, so we mentioned there are many different ways to generate electricity. Almost all of them involve different ways of spinning the turbine. All right, let's look a little bit more in detail here at how they spin the turbine. Right, so how can we spin that turbine? I mentioned some of the different options that we have. You could use coal. Right, so you take coal, you burn it, you boil water until you get steam, and then you take that steam and you focus it on your turbine and you spin the turbine. You could do the same thing with natural gas or petroleum gas. We say that all of these are non-renewable sources. Right? Non-renewable means that they will eventually run out. There's a limited amount of coal in the world and eventually will run out. Coal will eventually be formed again, but coal takes tens of thousands of years to form. So if you use it, it's going to take a very long time, well beyond your life, before more coal is formed. So these things, coal, natural gas, petroleum, there's limited amounts of it. We say that they are non-renewable things. And generally, all three of these also have concerns on on causing global warming, causing climate change. Why are we still using them? Well, they're generally cheap to find, to mine. They're transportable, right? You can mine the coal in one area and ship it somewhere else, or same thing with the petroleum. Right? So they're portable, they're easy to move, they're generally cheap still. What are some other options we have here? Oh, instead, you could just attach that turbine to a wind turbine, right? Just have the wind spin it. Or hydroelectric, right? That's where you build a dam and you block the water and then you allow it to go past your turbine and spin it. Right? If you can focus that water and just spin your wheel around your turbine, that also works. Or geothermal. Geothermal is where they dig deep down into the ground. The deeper you go, the warmer it gets, and they can use the heat from deep in the earth to boil water or steam, create steam, and then take that steam and spin the turbines. Geothermal generally depends on the area. Some areas they have much more heat closer to the surface, so geothermal only works in some areas. Now, these three things, we call them renewable sources. Renewable meaning that they're always there. They just keep replenishing, right? There's always wind and there's always flowing water and there's always heat deep in the earth. So they will never run out, right? The reason that we have flowing water and wind is because of the sun, right? And the sun is going to be around for a very long time. So we'll just continue to get wind and flowing water. So these ones are renewable. Right? We can just keep using them. Now, these are becoming more and more popular, but there are some downsides with them, right? You can't, on a windy day, you'll generate lots of energy, but not on a day where there isn't wind, right? So in this case, it's not reliable. Hydroelectric is nice because you can actually block the water and kind of store some of it up, right, until your dam is full. But they're extremely expensive to build, right? You have to block a river and build a gigantic dam. So these are extremely expensive to build. But the basic idea with all of these things, right, whether it is burning coal, burning natural gas, burning petroleum, harnessing wind or water, these things all end up taking that movement and spinning a coil of wire past a magnet. The magnet pushes the electrons in the wire. Now you have moving electrons in your wire and you have electricity. That's what electricity is. And then it's just a matter of getting it to people's houses or wherever it needs to be used. Now, we actually have a hydroelectric dam here in Ottawa, and you can look at it on Google Maps. So I've pulled up Google Maps here. Here's Green Wilson over here. And here we are downtown. Zoom in on downtown here. Here's Parliament Hill. And right over here is a hydroelectric dam. So I'm going to go into the satellite view and we can actually have a look at it. So you'll notice here they have blocked off the river. And you'll notice this white part here is flowing water, where they're actually focusing the water in order to spin a turbine and create power. I think we can take I think you can even do a little 3D view here with Google Maps. And there you go. So there's a hydroelectric dam nice and close to home here in Ottawa. You notice they've blocked it off there. They can allow the water to flow through, or they can block off more of it depending on how much power needs to be generated. They spin turbines with it, and then they have power. They have moving electrons, they have electricity. And I think we can, there's kind of a nicer picture of it there.